So, good morning, students. Today we will discuss about the quantum mechanical explanation for the Raman lines and also Rayleigh lines. So, without killing so many times, so directly come to the points. So, as we know, as from the qualitative quantum viewpoints, the occurrence of the Raman lines may be understood as follows. So, before we start, I can add some more lines because we know that when you use quantum mechanical discussion or quantum mechanical explanation, that means the energy levels are, you assume, that are quantized. So based on this concept we will explain accordingly. The photon colliding with the molecule will constitute either an elastic or inelastic collision, that we already know. We may consider a molecule to form a complex with the photon during this extremely short lifetime of as short as 10 to the minus 15, that is 1 femtosecond. The energy of the complex will not correspond to the molecular electronic energy level. That means after colliding with the photon, the molecule does not excited to the so much higher level that it will change its electronic energy state within the same electronic energy states. Okay. Now if the collision is elastic, the complex will dissociate immediately to give the molecules and the photon of the same energy which it had before collision. This gives rise to the Rayleigh scattering, because in Rayleigh scattering there is no change in the energy of the photon incident and the scattering photons. Okay. On the other hand, if the collision is inelastic, there occurs a an exchange of energy between the molecules and the photon. This exchange of in energy can be of two types. So first I'd like to show the picture of types 1, which is for Stokes lines. So initially the molecule is present in the vibrationally or rotationally ground state, and after colliding with the incident photon, that is h nu I, it will promote some virtually excited state, and when it returns back to the ground state, it will not directly come to the ground state. Initially that it directly not come to the v equal v0 state, rather it is staying in the v equal to 1 state. That means the emitted photon or scattered photon have energy less in comparison to the incident photon, which I can say again the molecule gains some energy, because initially it has energy is in that level, and right now it has energy in that level. The molecule before collision occupies a lower vibrational or rotational level. So type 1, the molecule before collision occupies a lower vibrational or rotational levels, and after the collision of the photon, it may present in any one of the higher energy level as permitted by the selection rule. In this case, the molecule gains energy equivalent to the energy difference between the two involved levels. This energy is provided by the photons, and hence its energy, that means the scattered photon energy, is decreased, and thus a Raman lines on the low frequency side is observed, and this is called Stokes lines. We have already discussed about the Stokes lines. Delta nu is less than 0. Okay, but mind it, the intensity of the Stokes lines is always higher, as the molecule initially present in the v equal to 0 state, and at normal temperature or room temperature it has the highest probability or maximum population in that level. So transition always takes place with a higher probability from v equal to 0 state. That's why the Stokes line intensity is higher. In type 2, the molecule before the collision occupies one of the higher vibrational or rotational levels that I can show from here. So initially the molecule at v equal to 1 state, and it's promoted to the some virtually excited state. When it returns back, it's not coming to the v equal to 1 state, rather v equal to 0 state. So v equal to 0 state, that means the molecule, the scattered photon gains some more energy. If the scattered photon gains more energy, that means the molecule loses energy, and in that case delta nu is greater than 0, and this is called the anti-Stokes lines. And the middle picture gives you the Rayleigh scattering situation, where the incident light comes with energy h nu I, interact with the molecule which is initially present in v equal to 0 level, promoted to some virtually excited level, and when it returns back, exactly return back to the same level. That means the emitted photon also have the same frequency nu I. That's it, there is no change in the frequency of the light, and this is called the Rayleigh scattering. So in that case, the molecule loses energy equivalent to the energy difference between the two involved levels. That means between the two involved levels, this energy is gained by the photon, and hence its energy is increased, and thus a Raman lines on the high frequency side is observed, and this is called anti-Stokes lines. And here also I will add some more lines, because anti-Stokes lines are always less intense than the Stokes lines, because we have know that the population of the v equal to one state at normal temperature is very less in comparison to v equal to zero state, so there is always a less transition probability from v equal to one state. That's why we